For a long time, generating realistic human speech or music was a massive challenge for computers. Traditional methods often sounded robotic or required stitching together thousands of tiny recorded fragments. This changed with Wavenet, a deep neural network designed to generate raw audio waveforms directly. Unlike previous models that relied on simplified acoustic features, Wavenet models the probability of every single audio sample. Think about that. At a standard quality of 16,000 samples per second, the model must predict thousands of values just to produce 1 second of sound. This approach is fully probabilistic and autoregressive, meaning each predicted sample depends on every single sample that came before it. By operating at this granular level, Wavenet captures the subtle nuances of human breath, mouth movements, and complex musical textures that older systems simply ignored. It represents a fundamental shift from simulating sound to generating it from scratch. To generate audio sample by sample, the model must respect the flow of time. Wavenet uses causal convolutions, which ensure that the prediction for a specific moment only depends on past data, never the future. However, standard convolutions have a limited receptive field, meaning they can only see a tiny fraction of a second behind them. To fix this without needing hundreds of layers, Wavenet introduces dilated convolutions. In a dilated layer, the filter skips input values with a certain step, allowing it to cover a much larger area of the audio signal. By doubling the dilation factor in each layer, going from 1 to 2 to 4, and so on, the model's receptive field grows exponentially. This allows a relatively shallow network to capture long-range temporal dependencies, such as the flow of a sentence or the rhythm of a melody, while remaining computationally efficient enough for training.
Raw audio is typically stored as 16-bit integers, which means there are over 65,000 possible values for every sample. Modeling a probability distribution over that many values is computationally expensive. To solve this, Wavenet uses a categorical distribution with a softmax layer, but first it reduces the complexity of the data. The researchers applied a mu-law companding transformation, followed by quantization to 256 possible values. This nonlinear quantization is clever because it preserves more detail for small amplitudes, where the human ear is most sensitive, while still significantly reducing the number of values the model needs to predict. Interestingly, the researchers found that even with only 256 values, the reconstructed signal sounds almost identical to the original. This transformation turns a massive regression problem into a more manageable classification task, allowing the model to be more flexible and capture arbitrary distribution shapes without making rigid assumptions about the audio's behavior.
The internal engine of Wavenet relies on gated activation units, similar to those found in high-performing image generation models. Instead of a simple ReLU function, Wavenet uses a combination of a tan-H and a sigmoid function. This gating mechanism helps the network control the flow of information through its layers more effectively. To allow the model to become truly deep, the architecture also incorporates residual and skip connections. Residual connections allow the network to pass information directly from one layer to another, which speeds up convergence during training. Skip connections, on the other hand, gather the processed features from every single layer and combine them before the final output. This ensures that both fine-grained local details and broad global patterns are considered when the model makes its final prediction for the next audio sample. Stacking these blocks creates a powerful model capable of learning highly complex structures. One of Wavenet's most powerful features is conditioning. By feeding extra information into the model, we can guide the generated audio to have specific characteristics. There are two types, global and local. Global conditioning uses a single value, like a speaker ID, to influence the entire audio clip. This allows a single Wavenet to learn and mimic many different voices. Local conditioning is even more precise. It uses time-varying features, like linguistic data or pitch contours. In text-to-speech applications, we provide the model with features derived from text.
Because Wavenet is trained on raw audio, it doesn't just learn the words, it learns how a specific speaker breathes and pauses. If we don't condition it on text at all, it generates babbling, sounds that have the texture and intonation of human speech, but consist of completely made-up words. This demonstrates just how deeply the model understands the underlying structure of human vocalization.
How does Wavenet compare to existing technology? To find out, researchers used mean opinion scores, where human listeners rate the naturalness of speech on a 5-point scale. In both English and Mandarin, Wavenet outperformed all previous systems, including the best parametric and concatenative models. In English, Wavenet achieved a score of 4.21, significantly closing the gap with natural human speech, which sits at 4.55. Beyond speech, Wavenet was also tested on music. When trained on solo piano or orchestral datasets, it generated highly realistic musical fragments. While it struggled with long-term structural consistency over many minutes, the second-to-second texture and harmony were remarkably convincing. The model has even been adapted for discriminative tasks, like phoneme recognition, where it achieved an 18.8% phone error rate on the TIMIT dataset, proving that a generative understanding of audio is incredibly useful for understanding it as well. Wavenet represents a major milestone in artificial intelligence. By abandoning the rigid assumptions of traditional speech synthesis and instead modeling raw audio waveforms directly, it unlocked a level of naturalness that was previously thought impossible. Its architecture of dilated causal convolutions has since influenced a wide range of fields beyond audio, from time series forecasting to natural language processing. Today, the principles introduced by Wavenet power many of the digital assistants and voiceover technologies we interact with daily. As we look forward, the ability to generate high-fidelity, expressive audio from scratch opens doors for more immersive virtual environments, personalized accessibility tools, and even new forms of creative musical collaboration. Wavenet didn't just give computers a voice, it gave them a way to understand the very fabric of sound. Thank you for watching this overview of one of the most influential models in modern machine learning.